if you were born within the last 20 years, you can be easily forgiven for thinking that the only kind of wired connectivity the computer industry used is Ethernet, or Ethernet if you like, as it's become dominant basically everywhere. Local network, use Ethernet. Long-range stuff that would have been the WAN technology, yeah, we now all use Ethernet. Available in speeds from 10 megabit to 100 gigabits a second. But not that many years ago, Ethernet's ascension was not guaranteed. In fact, another technology appeared, ready to work around many of the shortcomings of Ethernet and maybe even take over the market. I mean, it didn't. But that technology is called Token Ring. But before we get into the history of Token Ring and the whys and wherefores, we're going to have a quick word from our sponsor who helped make these videos possible. Yes, PCBWay, fine purveyor of PCBs. They also do other stuff like 3D printing, CNC machining, and make injection molds as well. Now back to the history of Token Ring. In order for us to understand what was so great about Token Ring, we have to understand the shortcomings of the things Token Ring was intended to replace. Ethernet, and in fact a bunch of other competing network technologies, were all based around the concept known as carrier sense multiple access with collision detection, which is quite a mouthful. Now in older networks based around this technology, there's what's known as a shared bus or shared medium between the machines. As in the case of Ethernet, this was typically one thin piece of coax that went from one machine to the next to the next to the next, with little T-pieces allowing each individual workstation to join on. This essentially means that all the machines are transmitting onto the same wire, and they're all listening to the same wire. So in a typical scenario, one machine would transmit onto the wire, all the other machines would receive those transmissions, and they'd check to see if it had the right address for that workstation, the MAC address. If it did, then it would take that packet and it would pass it up to the machine that the card was plugged into. Nice and simple, right? Although some of you have probably spotted the really obvious flaw in this situation, which is what happens when two machines transmit at once. And if two machines do manage to do that, well, what you end up on the cable is unintelligible gibberish. So this is a situation we need to try and avoid. And this is where the first part of that carrier sense multiple access thing comes in. Yes, this is the sense part of it. So all the time, every single network card in the network is listening to see if there's any incoming packets traveling along the network. And if it wants to transmit, it waits for a moment when there's no incoming packets. This is the sense bit. If the network is clear, it can then transmit. Absolutely flawless scheme, right? Nothing could go wrong. I think my tone probably gives away that that's not entirely true. That's where the next part of the giant phrase carrier sense multiple access with collision detection comes in. Yes, this is the with collision detection part. If two machines transmit at once, we call that a collision, so hence the phrase collision detection, which is when we need to sense when that happens. Now you may be thinking, but how can this happen? You've just told me it waits until the network is clear before it sends. Well, this is the small flaw. A network consists of multiple nodes, and if a few of those nodes all want to transmit at the same time, well, they're all listening to the same network, and the second there's not a packet on it, yep, they all try and transmit at the same time. So we need to detect when that's happened. Now doing that's actually pretty easy. Whilst the network card's transmitting, it's also still listening to the network, and if the bits it's transmitting happen to match the bits that it reads from the network, then you know you're the only one transmitting. If what you get back is different from what you're transmitting, well, then you know another network station is trying to transmit at the same time, and you've got a collision, and you've just successfully detected it. Now you know there's been a collision, you have to decide what you're going to do with it, and this is the approach that Ethernet adopted. In the event of a collision, all the machines that would try and transmit back off for an arbitrary period of time. A small period of time, but a small random one. Once that period of time has expired, the network card again listens to see if the network is clear, and if so, transmits. The idea of this approach being that one workstation will have the shortest timer and therefore go first, stopping the others from then transmitting. With this approach, eventually, every single node on the network gets to transmit its packets. The key problem with this is the phrase, eventually. The problem with eventually is eventually could be a small eternity as far as a network card's concerned. As on a busy network, with lots and lots of nodes, well, there are a lot of collisions, which means you could be waiting a very long time to get a packet in or out. Let me give you a practical example of that. When I was at university, our department had a number of PCs that were remote boot machines. You had a little boot disk for them that essentially contained a copy of DOS, a packet driver, and a TCP/IP implementation, and an NFS client. And your machine would boot up, load those, and NFS mount some remote storage from one of the Sun machines. If you're just in the lab by yourself, once the disks are booted, that process could maybe take 30-40 seconds to get to the point where you had a command prompt and you could start doing stuff. In a lab session, however, when there were 30 or 40 of us all trying to boot the machines at the same time, well, things were very, very different. It could often take you nearly 20 minutes to get to the point where you were logged in, storage was mounted, and you could start typing commands. And that's because the whole network essentially degenerated into mostly collisions. Very little useful data moved, and the collision count went through the roof. Now, I have glossed over a few of the details of this little problem. I mean, we've not really talked about things like the channel capture effect. And I did miss out little implementation details like the jam signal and preambles, as those things aren't really necessary for understanding the core of the problem that Token Ring was trying to solve. Yes, which that means it's now time to talk about Token Ring. Token Ring was a LAN technology created by IBM, and was standardized as IEEE 802.5. Now, Token Ring avoids the whole collision problem completely. There is no such thing as a collision in a Token Ring network, and there's a reason for that, and it's also where the token part of Token Ring comes from. The system operates much like the conch from Lord of the Flies. See, this channel's surprisingly literate sometimes, in that if you don't hold the token, you can't transmit. And the token is passed from node to node around a ring. See the other part of the name. If you don't have anything to transmit when you get the token, then you simply pass it on to the next station. If you have something to transmit, you hold the token, transmit your packets, then release the token. In this system there is also a maximum token holding time, which a node can only hold a token for so long, so it doesn't get stuck with one station and it do all the transmitting. Basically every node gets their fair share. Now, this system of using a token has some great advantages. Firstly, no collisions. This means all the network's bandwidth gets used for something useful. We don't have large amounts of times where no one can transmit and nothing useful is happening on the network. Our next major advantage is the predictability of this network as well. If you add more nodes to the network, you can work out how much bandwidth in the worst case those nodes are going to get. Take the total bandwidth, divide it by the total number of nodes, there you go, that's the worst case that each node sees. In Ethernet, that's not true, because most of the bandwidth may end up getting lost on collisions, and also that bandwidth is in no way evenly distributed amongst the nodes on the network. Now, to this point you may be wondering to yourself, so why didn't Token Ring become the dominant LAN technology? It's clearly got a lot of advantages over the likes of Ethernet. Well, as I alluded to in the title, comparing this thing to Betamax, better doesn't always win. Sometimes technically better still loses, and in Token Ring's case, yeah, it didn't win, did it? The problem for Token Ring is there's quite a lot of complexity in Token Ring. First of all, you have this whole token passing system that adds an amount of complexity, but also there are a lot of weird corner cases that bump up the expense and complexity of Token Ring as well. For example, you have to deal with what happens if someone turns off the machine that's currently got the token. Yeah, in the way I described how Token Ring works, I didn't mention what we do with that at all. You could just assume from my description that the network would just break at that point, which obviously is not something they could allow to happen. No, there is in fact a whole election system to work out which station effectively acts as the token monitor. The token monitor, then if it doesn't see the token appear after a certain amount of time, generates a new token and put that one onto the network. And of course you have to deal with what happens if the token monitor disappears. Well, you keep having elections until eventually you have a winner. All that complexity based around elections and monitoring the token, yeah, that all adds expense. There's a lot more complexity in a Token Ring network card than there is in an Ethernet one. And as we all know, complexity equals expense. Token Ring again was also more expensive due to the whole ring nature of things. You couldn't just plug a Token Ring card into a network. It didn't just go on a BNC connector like you did in early Ethernet, or just plug in a quick RJ45. No, in Token Ring at the center of the network is a semi-intelligent box that when you plug your card into it, using its drop cable, it negotiates joining the ring. This means with every Token Ring network, there's an expensive looking box in the middle. Now admittedly, Ethernet became more like this as time went on, as we moved to first multi-port repeaters and then multi-port bridges and then eventually switches, with an expensive box in the middle of the network, but the cards still remained very cheap. In 1985, IBM launches Token Ring into the marketplace, with a channel bandwidth of a whole 4 megabits a second. Yes, this does negate some of the advantages of Token Ring versus Ethernet, because Ethernet's got 10 megabit bandwidth, and even if it's using it very inefficiently and colliding a lot, 10's still quite a lot bigger than 4. But it is still very predictable compared to Ethernet when you increase more nodes in the network, and with big corporations, that sort of thing's quite popular. Having a predictable network kind of equates to having a reliable network in some ways, particularly where you don't want to get engineers involved on a regular basis, which is kind of what large corporations want. They don't mind if the unit cost is a little bit higher, as long as the maintenance costs are lower. Also, IBM at this point are huge. There are plenty of corporations that are just pure IBM shops. They buy all their PCs from IBM, their printers from IBM, their mainframes from IBM, their terminals from IBM, everything from IBM. So when IBM turns up with a LAN technology saying, look, see, you can use this to link your PCs together, and also, look, we've got stuff for our mainframes, even a 3270 terminal with a token ring interface on it. Yeah, that's going to do pretty well. Also at this point, LAN technology is fairly new. There's not an awful lot of LAN deployments in the world. In fact, in the UK, the biggest technology deployed for LAN networking is Acorn's Ethernet to link BBC micros together at schools. Yeah, unless you watched one of my other videos, you didn't see that one coming, did you? So initially, Token Ring is doing alright. It's selling in sufficient quantities. I mean, Ethernet probably still selling more, but neither of them is exactly a runaway success. Now, of course, IBM are not the only vendor of token ring cards in the world. In fact, quite a few other vendors for a relatively short period of time all start making token ring cards. But of all the other vendors, one particular one, Mage Networks, becomes the big second source of token ring kit. And towards the end of the life of Token Ring, it's just IBM and Mage making stuff. As the 1980s marches on, competition starts to get a little bit more heated. Ethernet continues its drop in price. The cards are starting to get cheaper, particularly with stuff like the NE2000 from Novell, and then the gazillion clones of the NE2000 that appear afterwards. The price point of an Ethernet card is starting to drop. Also, the usage of LAN technology is starting to grow. Again, the likes of NetWare really helps push this forward to give you a file and print service. So you get small SMEs starting to develop the use of LAN technology, rather than companies that had mainframes are looking to network a few PCs together. This means that the number of Ethernet installations are really starting to outnumber the Token Ring ones. So, in order to address one of the perceived disadvantages of Token Ring, its speed, we get a new speed of Token Ring. We get a 16 megabit Token Ring in 1989. It's this period after the introduction of 16 megabits that Token Ring has its most successful phase. It's during this period that Token Ring carves itself out a nice little niche for itself. It becomes the high-end networking technology of choice for LAN deployments. And it's this niche that IBM and Mage seem to feel quite happy with. You can charge a relative premium for your network cards and kit, and for a number of network-attached peripherals that also have Token Ring interfaces. IBM also brings out a bridge box that allows you to connect Token Ring networks with cheaper Ethernet networks. Now this brings me on to a point that I've previously not mentioned, the compatibility of frames between Ethernet and Token Ring. At layer 1, electrically, these two networking standards are in no way compatible with each other even slightly, but the frame you send across the network, that source MAC, destination MAC, what kind of data type it is, packet, yeah, that is actually compatible between the two. In fact, it's compatible between all the 802 whatever standards. So hence you can pass a frame from Ethernet to wireless's 802.111. The layer 1 format, completely different, the layer 2 format, the same. So this meant you could happily interchange packets between a Token Ring network and an Ethernet network, assuming you had the right box with a Token Ring interface in it and an Ethernet interface in it. In fact, in the very early days of wireless, you did also get Wi-Fi boxes that happened to have a Token Ring interface as well. They weren't very common and they were very expensive. It's from this period that all my Token Ring equipment essentially comes from my Mage network cards, be them either PCI or EISA. Yeah, there's a bus type you don't see very often. Or the portable ones that you'd have for laptops, like this PCMCIA one, or, if you're feeling really unlucky, the parallel version here. Yes, laptops back then tended not to come with their own network interface, either be it Token Ring or Ethernet. And I've got it all connected up to this Freecom Ring hub here. Yes, this may look like an Ethernet switch, but it's not. It's a Token Ring MAU. In fact, I've even got this machine here connected up with a Token Ring interface. And here we go, we've got a vulnerable Cisco router. Yes, I can have a bit of IP connectivity to the Token Ring network. Oh look, I can ping the router. Yes, it's not actually plugged up to the internet, because that would have been a little bit more complicated. And besides, pinging one thing on the internet and pinging something on the local network, yeah, they kind of look very similar, don't they? Yeah, I'm running a version of Linux from 2013 on a machine from 2006. Yeah, I did use this laptop for quite a while. Did have a more period-appropriate IBM laptop I could have used, but can I find the power adapter for it? No, not anywhere. Whole laptop? Yeah, I can find that. It's worth noting, This particular token ring card, yeah, still actually supported in the Linux kernel to this day. But at the time, this driver CD that you can cut back to, yeah, that had drivers for sort of Windows, DOS, Windows 2000, so on and so forth. And of course, the NetWare client. Also during this peak period for Token Ring, cable standards are evolving somewhat. Now initially IBM starts with this kind of connector for Token Ring. Yeah, it's a bit of a monstrosity, isn't it? It's not the most attractive connector you've ever seen, or the most compact. But this is what IBM go for on the sort of connect to the cow at the centre of each token ring, or indeed the wall sockets. In terms of the end that goes into the computer, well, they go with a DB9 of all things. Yes, the thing that looks a little bit like a joystick or a serial port, that was the initial connector that you would use. Of course, things change and everything starts moving to RJ45 and Cat5 sockets, and this is being driven by the exact same thing that was driving Ethernet the same way, in that lots of buildings in the US already had this kind of cabling installed for office telephone networks. So as they'd already flood cabled the building, once computers start expanding outside a couple of departments into everywhere in the office, well, there's a need to want to use the pre-installed cabling. So this is one of these cases of co-evolution, where two different technologies evolve in a similar direction because they both have the same needs and wants. So Token Ring's little niche being the high-performance, predictable network, that lasts for a while, until we get to 1995 and things start to change a little bit. As while in the world of Ethernet things have just continued to get cheaper and cheaper, there is suddenly a big leap in its technical capabilities. This is when the 100 meg standard for Ethernet first appears. Now, even if you do still have the collision problem, 100 megabits of channel bandwidth is a heck of a lot more than 16. So let's say you lose 20% of it to collisions, you've still got a lot more megabits a second than the 16. This really sort of damages the sheen on Token Ring, if you like. It's not quite seen in the same way anymore. It looks like Ethernet's starting to get a leg up on it. Now, of course, those involved in producing Token Ring cards, they don't take this lying down. They do eventually produce a 100 megabit Token Ring standard in 1998, a full 3 years after 100 megabit Ethernet is introduced. And to be honest, not a heck of a lot of 100 megabit Token Ring cards are actually produced. I've got one here. They're not really common, it must be said. Most people sort of stayed at 16 and then moved on to Ethernet afterwards rather than going up to 100 megabit Token Ring. In another bit of bad timing for Token Ring, 1998 was also the same year that Gigabit Ethernet came out. So while Token Ring's just getting its 100 meg, Ethernet managed to go 10 times faster. Now, given that Token Ring's niche in the market is the high-performance, high-price, dependable network, having Ethernet, which was seen once as the cheaper option, and it still is cheaper, go faster than you go, is not great. And this is the point that really marks the steep decline of Token Ring usage, although you will still see it in use in some sites. Lots of large corporations still have it in their warehouses and stuff like that, where they have a bunch of IBM kit and still have Token Ring there, still getting on and doing its thing, of equipment that's just too expensive to be worth replacing, really. Now, I know some of you are particularly clued up in the world of Token Ring, might be thinking, wait a minute, wasn't there a gigabit standard for Token Ring? And there was. In 2001, they released a gigabit standard, and then promptly, no one built a single piece of equipment that implemented it. Yeah, unfortunately by 2001, very much everyone knew that the game was up for Token Ring, as, well, Ethernet had kind of taken over everything. And also, Ethernet had solved the one big problem that Token Ring was also there to solve: collisions. Yeah, it's time to talk about the final nail in the coffin of Token Ring, the Ethernet switch. Now, as I mentioned earlier, cabling solutions for both Token Ring and Ethernet had been changing to the idea of a star topology, essentially a couple of boxes in a central room somewhere that every other device would individually connect to, via a cable back out to that workstation. And in order for Ethernet to achieve this, there'd been a whole new connection standard known as 10 base T, 10 for 10 megabit Ethernet, and then T being the connector type at the end. So this is the RJ45 connector you're all very familiar with, no doubt. And at the centre of this network, they were going to need a new class of device for Ethernet to link this all together, and this is known as the multi-port repeater, or hub, as most people commonly refer to it as, and this is where you connect each individual Ethernet connection, and then everything linked together on the hub would be allowed to speak to each other, and you could plug one hub into another hub, and therefore linking even more devices. Now at this point, the hub, as I said, is a multi-port repeater, which is effectively a very dumb analog device. There is a small amplifier in there That essentially just amplifies the signal, because there's a longer amount of cable involved here, and a little bit of noise filtering circuitry, just to take any line noise off or reduce it a bit. These devices are completely dumb. There is nothing clever or digital going on in these things at all. So with these devices, you still have all the same collision problems you did before. So we've managed to change essentially the wiring standard for Ethernet, but we haven't really improved it. But we do now have the idea that there is a core box at the centre, and this is where things start to change. With the advent of these central boxes, you've now got a point where you can put some more sophistication into Ethernet, where you couldn't really before when it was just a thin wire. Now, we had gone this way a little bit with the introduction of something known as an Ethernet bridge early on in the life of Ethernet, which is essentially a box that had two Ethernet ports on it, both thin coax. And essentially this box was an intelligent box, and it had two Ethernet interfaces and would hold in memory a list of what MAC addresses were on one port and which MAC addresses were on the other port. If it saw a message on one interface that was from a MAC address on the other interface, well, it'd read that into memory, store it in memory, and then would transmit that back out the other Ethernet interface, essentially acting as a bridge between two separate Ethernet networks. It wouldn't repeat broadcast packets. This was a good way of getting around the cable length limits for Ethernet and still allowing stations to talk to one another. It also meant that you could reduce the number of nodes on each network as well and get the number of collisions down, if not eliminate them. Now, in 1993, a company called Kalpana came up with a really good idea, which was to take this bridge idea and make a multi-port bridge, but also add the idea of cut-through forwarding to create the world's first Ethernet switch. One of the disadvantages of a bridge is the latency, because you have to read the whole packet into RAM and then write the whole packet back out again. What cut-through forwarding meant that they could do is they could start reading the packet in, and when they detected the MAC address, they could start writing it out of the right interface straight away, assuming that it was free to transmit. This hugely reduced the latency involved. Now, these initial switches were hugely expensive and didn't, at that point in time, have massive impact on the market, because very few institutions could afford them, and essentially they'd use them to join together a number of existing Ethernet networks and make it a bit more efficient. Where things really kicked up a gear was when the 100 meg standard was introduced. This is where the switch became an essential part of your network rather than an optional extra, as it were. Because the switch essentially having a separate Ethernet network per port, it meant that you could connect ones running on the 10 meg standard to ones running on the 100 meg standard. As you could have a number of ports running 10 meg Ethernet and a number of ports running 100 meg Ethernet, and they could communicate with each other across the switch. Because now essentially you don't have one Ethernet network, what you have is one Ethernet network per port on the switch, and each one can be of an entirely different standard. And the switches were sufficiently sophisticated that, say, if ports 1 and 2 talked at their full data rate to each other, well, ports 3 and 4 could talk to each other at their full data rate too. And as each network basically consists of a node and the switch, well, there's not much chance of a collision, is there? And also with 100 meg they introduced what's known as full duplex, where a port could transmit at full speed and also receive at full speed, and that reduces the chance of a collision down even further. So essentially the switch has eliminated collisions. This means that the final advantage of token ring, the lack of collisions, basically evaporated. So this is why the switch is basically the final nail in the coffin of token ring. It's taken away its one final advantage. It lost its advantage over speed, and now it lost its advantage over predictability and the lack of collisions. Now, it's not like token ring vendors don't try and fight back at this point. The likes of Mage, for example, soon produces a token ring switch, which is basically the same idea as the Ethernet switch, with each port being one token ring network. The problem is, with token ring adapters being so complicated, they never really fall in price, so it's just a very expensive way of doing more or less the same thing that Ethernet does at this point. Yeah, Ethernet's great advantage of the cheap network adapter really starts to cut in at this point as well. Because of its lower implementation cost, it starts to appear in machines. Not as an optional extra card that you fit, but right there on the motherboard, same with laptops. Which up until this point, you had to have a PCMCIA adapter to do either token ring or Ethernet, depending on which one you wanted. Now with everyone seeming to think that the network standards war is over and Ethernet has won, machines just start coming bundled with Ethernet adapters just built right on in there, which really makes life difficult for token ring because you got to persuade someone to buy an additional network card. And unless your company already has a big token ring infrastructure that you want to join, why would you do that? If you made it all the way to this point in the video, I'd like to say thank you very much for watching.
I do apologise for my ever so slightly strained voice, but it's still recovering a little bit from the event at Cambridge I went to at the weekend. If you want to see what that event is like, Kim Justice has done a really nice video about it. I will link that in the comment section below. If you enjoyed this video, why not inform YouTube that you did by clicking that little thumbs up button they included to indicate that such a thing has occurred? And if you're feeling in a kindly mood, why not share this video with other people that you think might be interested, because that does wonders for the YouTube algorithm. Speaking of things that do wonders for the YouTube algorithm, you could always click that cheeky little subscribe button if you hadn't, because again, that helps the YouTube algorithm acknowledge that this video actually exists.